Welcome to this first lecture of EE404 after the coronavirus. I hope all of you are actually okay, and I hope that your families are okay as well. I'm fine so far, a little bit worried though, so I hope we will get rid of this virus pretty soon. So in this first lecture of EE404, I want to actually review first what we have done so far in the course. It is going to be mostly a review lecture, and only the last 4 or 5 pages will be some new material. So I hope you can actually print these notes yourself and you can study from them with the help of these audio lectures. So I will first go over the material that we have covered so far, and then I will repeat the last lecture that we have done about describing function analysis, and then I will add some material, some new material at the end of that. So the brand new lectures will come after this introductory lecture. So let us look at what we did in the course so far. So we started by defining what linearity is. Of course, if you're taking a nonlinear control course, then you have to know what linearity means or what nonlinear systems do not actually satisfy. Then we looked at the state space and differential equation representations of nonlinear systems, and we have seen some conversion from the differential equation to state space representations. Because most of the time, nonlinear systems are actually analyzed in state space form. So then we looked at types of nonlinear systems, and in that we have defined what an unforced nonlinear system is, what time invariant and time varying nonlinear systems is, and what both unforced and time invariant nonlinear systems would be, which are called actually autonomous nonlinear systems. Then we have seen the equilibrium points of nonlinear systems. We have worked on both autonomous and time invariant nonlinear systems. In the autonomous case, any x value which would make the right hand side of the differential equation equal to 0 actually is called an equilibrium point of the system, and if the system will remain at the equilibrium point, if it is actually at the equilibrium point. And for the time invariant nonlinear systems, equilibrium points are defined with the equilibrium inputs. We consider constant equilibrium inputs, and xe values which make the right hand side equal to 0 would be called equilibrium points for that equilibrium input. So therefore, the equilibrium points of time invariant nonlinear systems would depend on the equilibrium input that you select. So then we have seen the important topic of linearization, and we covered again both autonomous systems and time invariant systems. In the autonomous case, we linearize the system around the equilibrium point, and we get a new equation which is linear with the new state variable. So I have z that is equal to f of x, and z is defined as the deviation of the state x from the equilibrium point, and f is the Jacobian here evaluated at the equilibrium point. For the time invariant systems, we obtained a similar result, except in this case we have a new input term, and we defined a deviation from the equilibrium input, and we now have the partial derivatives both with respect to x and u here for obtaining these matrices here. Then we went into the second order systems and phase plane analysis. So you know that the phase plane is called, the state space is called the phase plane in nonlinear control, and we looked at just the linear systems first, and we characterized or classified the equilibrium points of linear systems. If a linear system has an isolated equilibrium point, then it has to be at the origin. So then we try to classify what origin is with respect to the eigenvalues of the A matrix. Remember, if both of the eigenvalues, so this is for the second order systems, if both of the eigenvalues are real and they have the same sign, then we call the equilibrium point a node type of equilibrium point, and the trajectories around them would be in this parabolic form actually. So these are the eigenvectors of A matrix. The second one is not shown in a good way here, but there is a line here. And we call and on these eigenvectors, the state trajectories would remain if they start on them, but everywhere else we are having parabolic trajectories here around the equilibrium point. Since this is a linear system, this behavior is actually a global behavior. And if the eigenvalues are positive, then the motions are actually getting far away from the equilibrium point, and we call the equilibrium point an unstable node. On the other hand, if the eigenvalues are negative, then we have a stable node and all trajectories are converging towards the equilibrium point at the origin. The second type of equilibrium point that we saw was the saddle point, and this is the case when the eigenvalues are both real again, but they have the opposite sign. In that case, we see this type of hyperbolic trajectories actually, and here I have taken the E1 and E2. These are the lines corresponding to the eigenvectors of the A matrix, and the first eigenvalue is positive, so the motion on the first eigenvector is getting away from the equilibrium point, and the trajectories on the second eigenvector are getting towards the equilibrium point. At all other places, we observe these hyperbolic trajectories. And in this case, this equilibrium point is called a saddle point, and it is in general an unstable type of equilibrium point. So the third type was the case of complex eigenvalues, and in this case we have eigenvalues in the form sigma plus minus j omega. Because we are always considering a real valued A matrix, so the eigenvalues are always coming in complex conjugates if they have actually imaginary parts. So in this case we actually have a focus if we have just complex eigenvalues, or a center if the real part is equal to 0. If the real part is non-zero, we have a focus, and if the real part is 0, we have a center type of equilibrium point. And if the real part is positive, we have an unstable focus, so the motion is going to be getting away from this equilibrium point. And on the other hand, if the real part is negative, then we have a stable focus which converges to the equilibrium, around which all trajectories converges to the equilibrium point here. And we have the center, in which case we have a periodic motion around the equilibrium point when the real part is equal to 0. So then we looked at, though this was the case of linear systems, and we looked at the phase plane analysis of nonlinear systems around equilibrium points. In this case, we only have a local analysis, so we can only know sometimes the trajectories of nonlinear systems around their equilibrium points. And for this purpose, we are actually using the linearization of the nonlinear system around the equilibrium point. Then we look at the type of the equilibrium point for the linearized system, and then sometimes we can actually say something about the trajectories of the nonlinear system around the corresponding equilibrium point. So here, if the eigenvalues of f has all non-zero real parts, then we can actually say something about the equilibrium point, the trajectories around the equilibrium point of the actual nonlinear system. For example, if we have a node for the linearized system, then that means that the real parts of all eigenvalues are actually non-zero, which then this means that the trajectories of S1 will make the equilibrium point a node type of equilibrium point for the actual nonlinear system here. Or if I have a saddle point for S2, then it is a saddle point for S1 as well. Similarly, if I have a focus for this one, I have a focus for the nonlinear system. But you should remember that these are only local conclusions about the trajectories of the actual nonlinear system. If we are far away from the equilibrium point that we are considering, then we might have different trajectories than the node, saddle point, or focus type type of trajectories. And if we have a center for the linearized system, the real parts are actually equal to 0. So in that case, we cannot make a definite conclusion about the type of the equilibrium point of the nonlinear system. In that case, we know that it is a center or a focus, but we won't be able to know it with further analysis, for example, without using polar coordinates or any other analysis type. Then we went into, finally, in the phase plane analysis, we went into the concept of global phase plane analysis for nonlinear systems. And in this case, we are trying to draw globally the trajectories of the nonlinear system. So in that case, there are two methods, but these methods are all confined to very simple systems. So we cannot really analyze a complex, very complex nonlinear system without using a computer, the trajectories without using the computer. So the first method for global phase plane analysis is to cancel the time from the differential equations. And in that case, we are actually taking the ratio of both sides here, and we get a differential equation which doesn't include the time behavior, which is not necessary for the trajectory information actually. So then from this differential equation, which is only in terms of x1 and x2, we solve either x2 in terms of x1 or vice versa. And the second method was called the isocline method, because in this method we are actually trying to draw the location of the points in the state space on which the trajectories of the nonlinear system have the same slope. So we equate the right-hand side to alpha here, and we try different alpha values and solve for x1 and x2 values which satisfy this equation. And on the locations which satisfy this equation, we know that the trajectories would have the slope alpha. The next topic that we have seen in the course was the concept of periodic trajectories. You know that in nonlinear systems there are specific types of periodic trajectories called limit cycles. A limit cycle is just an isolated periodic trajectory, which means that around the periodic trajectory, you won't find infinitesimally close other periodic trajectories, which is actually the case in linear systems. So they don't have actually limit cycles. But in nonlinear systems, we can observe isolated periodic trajectories, which is sometimes quite useful and which is sometimes quite dangerous. So then we saw some results on existence and non-existence of periodic trajectories in nonlinear systems or linear systems, it doesn't matter really. So the first result was called Bendixson's theorem, and in that we used the divergence of the vector field associated with the nonlinear system to actually conclude that there are no periodic trajectories in a region for the nonlinear system. In that case, we had the divergence of the vector field f here, the right-hand side of the x dot is equal to f of x. If this does not change sign in an open set, and it's not equal to 0 in a subdomain of that open set, then we won't find any periodic trajectories in that region, in that open set. The second result was called the index theorem, and in that case we define these n and s numbers. These are the total number of nodes, focuses, and centers in which is enclosed by a candidate periodic trajectory, and S is the number of total saddle points of the system in a candidate periodic trajectory. And if this equation is not satisfied, then that candidate periodic trajectory cannot exist. So we have seen this type of non-existent results. There are two non-existent results, and these are the Bendixson's theorems and index theorems. The third result was an existence type of results, and it was called the Poincaré-Bendixson's theorem. So in that case, if we have a second order system, this second order was important, remember. If we have a second order system whose trajectory remains in a bounded region, and if there are no equilibrium points in in that region, then there should exist a periodic trajectory in that region. So we have seen in the class that there was a third order system which is called Lorentz attractor, and it really doesn't satisfy this type of theorem. Its trajectories remain in a bounded region where there are no equilibrium points, and still it doesn't have any periodic trajectories. So this theorem is only valid for second order nonlinear system. So now let us look at the next topic. This is most probably the last lecture that we have seen. So in this case we are again worried about the periodic trajectories of a nonlinear system, and we would like to predict whether there are periodic trajectories or not, and we would like to, if there are, we would like to predict their parameters, and we would like to also predict the stability or instability of the oscillations. So the describing function analysis is an approximate method, so anything we say is not really a definite conclusion. So without using a computer, we cannot actually confirm or deny these results, and we can determine the existence of periodic trajectories by using describing function analysis, and we can try to find approximate frequency and the amplitude of the oscillations using describing function analysis, and we can also look at the stability of the oscillations. I will try to explain what I mean by stability of oscillations. So in describing function analysis, we have a feedback system given in this form. In this case, a nonlinearity is connected with a linear system. So because of the nonlinearity, the overall system is actually a nonlinear system. And with this system, we would like to predict the existence of oscillations. So are there any oscillations in these variables that we can predict the parameters of? So therefore, if we don't have a system if we have a system which is not in this feedback form, in order to be able to use the describing function analysis, we have to bring it into this form. So we have a linear system which is somehow good, because the main idea of describing function analysis is to replace this nonlinearity with a linear system and use the linear control tools in order to analyze the behavior of this overall nonlinear system here. So we have some assumptions. For example, the linear system is assumed to be low pass here. So when I look at the frequency response of the system, I need to have the high frequencies should be attenuated more than the low frequencies here. Here the frequency response can be flat here around zero frequency, or it might go to infinity around zero frequency, depending on the pole positions of this linear system. So in class we have seen some candidate nonlinearities that we can analyze. The first nonlinearity was called the relay. It was just a switch. The second nonlinearity was a saturation type of nonlinearity, and the third type was called a dead zone, where we don't have any response from the nonlinearity in a region, and we start to get a linear response outside that region. So these candidate nonlinearities are actual examples of static nonlinearities. By static, we mean the memoryless. So here, when I look at this nonlinearity, for each E value, I have a single U value that is given by the nonlinearity. If the nonlinearity has some memory, then sometimes we might have multiple values for a single E value. And those nonlinearities are called dynamic nonlinearities, or nonlinearities with memory. In class, we have seen some dynamic nonlinearity examples. The first example was the relay with the hysteresis. This is still a switch, but it has a hysteresis behavior inside it. So we see that here, if E is somewhere in this region between -A and A here, the nonlinear element can give us multiple values depending on if E is increasing or if E is decreasing. If E is increasing, then the nonlinearity gives us plus B, and if E is decreasing, the nonlinearity is giving us minus B. Here outside this region, there are only single values. So therefore, in some way here, the behavior of this nonlinearity is dependent on the derivative of E, which means that this nonlinearity has some memory in it. So this is therefore a dynamic nonlinearity. We have also seen a second type of dynamic nonlinearity that is called backlash, and this appears in the motion of this type of gears, where there are some spaces between the cogs of the gears here. So in the course, we have actually, in the last lecture, maybe in the last half an hour, we have actually solved an example, and here in this introductory lecture I would like to go over it once more so that you remember the main ideas of describing function analysis. In this case, we have a system called van der Pol oscillator, and it is actually an oscillator here. So it is implemented with some circuit elements, but once you implement it, its differential equation is given in this form. So here we have a second order differential equation, and it is nonlinear because of this second term here. Here mu is a real parameter which is positive. So the task is to find the amplitude and frequency of oscillations and determine their stability, if the oscillations are stable or not. I will be talking about it. So since this system is not not in feedback form, I have to first put it into the feedback form in order to be able to use describing function analysis on it. So therefore, what I'm going to do is, in that equation, I will collect all the linear and nonlinear terms on each side here. If I collect some linear terms on the left-hand side, I have x double dot and mu times x dot here, there is a minus sign, plus x. These are all linear type of terms. This is equal to, I take the nonlinear term mu x square and x dot multiplication to the right hand side, and therefore I get this equation, and then I take this mu for convenience. I take this mu to the left hand side, which gives me this type of equation. On the left hand side I have all linear terms, and on the right hand side I have nonlinear terms here. Now I would like to use this equation in order to be able to put this system into the feedback form. So what I would like to do is to find a system like this, and I have to choose what f is and what g of s is. Here I would like to make this variable x, which is the same variable as my differential equation here. So then the question is, what is this f and what is this g of s here? So when I have an x here, I know that I have the reference 0 here, so I know that this e of t is going to be just minus x, and I'm going to try to equate the right hand side of the nonlinearity to the nonlinear terms in our equality here. So I would like to make this the right hand side of the nonlinear element f here by my nonlinear terms here in the equation. And I know that these nonlinear terms should be equal to the left hand side, so I need to have the linear terms here. So this linear system is nothing but a system which converts these terms to just a variable x here. So now this situation is easy to analyze. So I need to put here a nonlinearity which converts the variable minus x into variables minus x squared x dot, and I need to put here a linear system which converts the variables x double dot minus mu x dot plus x over mu into the variable x here. So the nonlinear system nonlinear element part is easy here. When I concentrate on the linear system part, for example, when I try to convert x dot into x, I need to use the linear system 1 over s. And if I want to convert x dot plus 2x into x, then I need to use here 1 over s plus 2. So then you can really guess which linear system in Laplace domain would be converting this variable here into x, and it's going to be just mu over, mu's are going to cancel, s square minus mu s plus just 1 here. So then I can actually write this. So I have minus x here, minus x squared times x dot here. So therefore this nonlinearity have to be, if I take the variable here to be e, and if I take the variable to be u here, then f of e is going to be e squared times e dot. Instead of e, if I substitute minus x, then I would obtain minus x squared x dot. And here I have my linear system. So now what we want in describing function analysis is just that we want this system to have sustained oscillations. So which means that there are some sinusoidal terms in these signals, E, U here and X. Here we are going to be selecting the variable E, and we would like it to actually oscillate with some amplitude and frequency. So in some way in the describing function analysis, we want E of t to be an oscillatory signal, which is given as E hat times sine omega t. Then we are going to obtain a sustained oscillations in this loop, which means that this sinusoidal signal is going to pass through the nonlinearity, and then it's going to pass through the linear system, and it's going to come back here in the same form as it is originally. So that means a sustained oscillations for the closed loop system. So in order to be able to obtain such a behavior, first we need to get rid of this nonlinearity, and describing function analysis does that by replacing this nonlinearity with some linear system, by making a kind of linearization in frequency domain. So here what we do is that we first set this E of t to be E hat times sine omega t, and then we calculate what U of t is, the output of this nonlinearity is. We do this by substituting E of t is equal to this one into our nonlinear element equation, and it is going to give me just this multiplication, which can be organized in this form. What I would like to do here, I would like to write this multiplication here in terms of pure sines and cosines, which means actually a Fourier series expansion. So, but here I'm going to do it not calculating by the Fourier series coefficients here. I will try to do it by using some analytical manipulations on the trigonometric functions. So here I know that sine square can be written as 1 minus cosine 2 omega t divided by 2, then substituting this into sine square here, I would obtain this multiplication, which gives me this type of terms. So I could get one cosine term here, one pure cosine, which is quite fine, but I still have the multiplication of cosines here. Now I can get rid of this multiplication as well by using this formula here, and it would give me just this in this case. So then just organizing the terms here, I would get the right hand side. This is like a Fourier series expansion, and the Fourier series coefficients are given by this one and this one here. So here we see that I have a cosine term which has the same frequency omega as the input. So remember, E of t was this signal here. So therefore I have the same frequency with the input here, and I have the 3 times the input frequency here. So I can from this analysis I can directly understand that this was without knowing the nonlinearity. If I know only the input and the output, I would have understood that this was a nonlinear element. This was actually a nonlinear element actually. So because here the input has some frequency, but the output has some additional frequencies in it, which is just a third harmonic here, 3 times the frequency. Remember that our system is actually linear and it has low pass characteristics. So therefore these high frequency components are actually going to pass through that linear system, which will attenuate these terms. So therefore here, what in describing function analysis, we are going to neglect all of these higher order terms, and we are actually going to be assuming that u of t is only composed of this term which has the same frequency as the input here. So when we neglect these terms, the output of the nonlinearity would turn out to be this single cosinusoid here, and then we are going to be asking the question, which linear system would give me this output when I have its input given as this? So I'm actually asking the following question. So I have E of t is E hat sine omega t, and the output is given by this. Then we are going to be asking which linear system here would have exactly the same output for the same input. So here we know that this can be actually a linear system because the output has the same frequency as the input. This is the behavior of the linear systems here. So in order to be able to discover that system, we can first consider which system converts sine to cosine here, because here the sine is converted into cosine, and I have an amplitude modification as well here from E hat to E hat cube omega over 4. But let us first look at what changes sine into a cosine. Which linear system does this? So when I take the derivative of sine, it gives me actually omega times cosine omega t. So if I divide the derivative by omega here, I would obtain the linear system which would give me a cosine from sine here. And in frequency domain, the derivative is nothing but j omega, and when I multiply it with 1 over omega, I get just j. So in frequency domain, the linear system which converts a sine signal to the cosine signal is represented by the transfer function, just j here, a 90-degree phase shift here. So therefore, when I consider here from sine to cosine, there will be a j in my frequency domain representation, and the amplitude change from this one to this amplitude here. And we are going to be calling this representation here, the system representation here, frequency domain system representation here, as n of E hat and omega. It is going to be in general a function of both E hat, the magnitude, and omega here. And I have my j here, and the division of the division of the output amplitude to the input amplitude here, which would give me just this result. So this result is actually called the describing function of the nonlinearity f. So we had the nonlinearity e squared times e dot, and this is what describes that nonlinearity in frequency domain. Of course, it's an approximate description, but it is some form of approximate description that we can calculate easily. So when we look at the Laplace domain representation, I can actually convert this j omega into an s, and then I can substitute it instead of into the nonlinear element block here in our original system. This is the actual linear system in my original system, and I replace the nonlinearity with its describing function here. As soon as I replace the nonlinearity with its describing function, I can actually apply linear control tools here, which actually what makes describing function analysis attractive. There are really many tools that we know for linear control, and describing function analysis enables us to actually be able to use them. So now I can actually take this S here into the linear system part. S is just another dynamic element that I can take into the linear system here. It is going to give me just the same system in the overall. So then I can actually call this new system as the linear equivalent of the original nonlinear system. And as you see here, I have the describing function e squared s over 4, s is here, and I have the other gain term here, and I call it to be k. So this, which makes this system quite similar to the systems that you have seen in 302, which is actually, in this case, a proportional control system. In the original nonlinear system, we want sustained oscillations. Now we want sustained oscillations in the linear system and linearized system here. So, but we know then what we have to do, because for a linear system to have sustained oscillations, we know that it has to have some poles, some closed loop poles, exactly on the imaginary axis. And that is actually what we are going to try to obtain here. I will try to find here the E hat value. This has to be E hat. E hat value, which actually makes this closed loop system have poles exactly on the imaginary axis. So remember the linear system theory here. So if I have a feedback loop here composed of the forward path transfer function g of s and feedback path transfer function h of s, the closed loop system transfer function is given by this ratio. And if I want this closed loop system to have sustained oscillations exactly on the imaginary axis, then I have to check the case when s is equal to j omega, and I have to try to find closed loop poles exactly on the imaginary axis. The closed loop poles of this transfer function are described by the denominator here, which gives me the characteristic equation 1 plus g of s h of s equals to 0. Any solution of this equation would be a closed loop pole, and since we would like to have closed loop poles on the imaginary axis, we substitute s equals to j omega here, and then we try to solve for omega. So this is my equivalent linearized system now. And if I write this characteristic equation here in this form, remember this k is equal to e hat square over 4, but I will keep it at the notation k for the sake of simplicity. And then what we are doing is that I want to solve this equation by substituting s equals to j omega. Let us first equate the numerators here, which gives me this polynomial equal to 0 here. Now I can substitute s equals to j omega and try to solve for k and omega values from this. So if s is equal to j omega, I have minus omega square here. The real part is 1 minus omega square, and the imaginary part would be just this. Since this is equal to 0 means that both the real part and the imaginary parts are equal to 0, I get omega square equals to 1, which has the solution omega equals to plus minus 1. And I have here either omega is equal to 0 or k minus 1 is equal to 0. Omega equals to 0 cannot happen because of the real part result here. So therefore I forget about it, and so therefore k has to be equal to 1. So therefore for this closed loop linear system to have sustained oscillations, I need to have k equals to 1, and I need to have omega equals to plus minus 1 here. So this actually gives us a frequency of oscillations equal to plus minus 1, and the amplitude of equations are determined by the equation k equals to 1, which gives me e hat. So since k is equal to e hat square over 4, this gives me the equation e hat square is equal to 4, and e hat has to be either plus 2 or minus 2. So then we have actually found the approximate amplitude and frequency of the oscillations of our system. Remember, in linear control, if you have poles exactly on the imaginary axis, then the imaginary part of those poles would be the frequency of oscillations. And here the same situation is actually, we have the same situation. Remember, in the last lecture, we have actually simulated this one dipole oscillator, and we have also seen that in the class that these parameters are quite close to the reality for the nonlinear system. So we have seen an oscillation period of around 6 seconds, which is actually predicted by this analysis here, and we had the oscillation amplitude equal to approximately 2. So far I have actually covered the material that we have already seen in the class. Now I'm going to, as a final and small point, I would like to show you how to analyze the stability of oscillations using describing functions. And in order to be able to do that, first we have to know what we mean by stability of oscillations. So here I show two figures to you, and in each case I have a pure sinusoidal oscillation in both figures. But these two oscillations, in terms of stability, they have different characteristics. So the first oscillation, we call it to be a stable oscillation, and the second oscillation is called an unstable oscillation. And the reason is as follows. In the first oscillation, if I make some perturbation, apply some perturbation to this oscillation, just a little bit, and pull the state inside, what is going to happen to the new trajectory of the system? In this system, we see that all of the oscillations inside this oscillation here are actually converging back to the original oscillation on this line. So if I start the system anywhere inside the circle here, close to the oscillation, the trajectory of the system, the dynamics of the system is going to take the trajectory back to the original limit cycle here. And the same is true here when we start the system outside the circle here. So if I apply a perturbation to the system such that the new initial condition happens to be outside the circle, I see that the trajectory is converging back to the limit cycle here. So therefore, infinitesimally close to this original oscillation, all trajectories of the system are actually converging back to the oscillation. So in that case, we call the oscillation to be a stable oscillation. So in the other figure, I have exactly the opposite case. So if I start the system very close to the original oscillation, but not exactly on the oscillatory trajectory, the trajectories are getting away from the oscillation. Maybe there is an equilibrium point here, and they're converging to that one. And similarly, outside the circle, if I start the system very close to the original oscillatory trajectory here, the trajectories are getting away from the oscillation. So therefore, this type of oscillations are called unstable oscillations in nonlinear control theory. Of course, for example, if we would like to build a clock, if we would like to have a radar which is a very stable and accurate, robust clock, in that case, the oscillation that is involved in the clock should be a stable oscillation, and it should be robust to perturbations from the main trajectory. So there is a third kind of oscillation, and that is called semi-stable oscillation. It is still an unstable type of oscillation, but sometimes it's called semi-stable oscillation. And in that case, outside the circle, the trajectories are converging to the oscillation, and inside they are diverging from the oscillation. Or I have the opposite case. Outside they are diverging, inside they are converging to the oscillation. So in some sense, in this case, we have stability behavior around the oscillation, around the two sides of the oscillations would be different. Outside they're convergent, inside they're divergent, and vice versa here. This type of oscillations are called semi-stable oscillations. But since we have divergence at least on one side, then we can call them as unstable oscillations as well. We can check the stability of oscillations using describing function analysis. And in order to be able to do that, usually these linear control tools are actually utilized. If the describing function is or the gain in the linearized system is real and positive, we can use the root locus plot to analyze the stability of the oscillations. And on the other hand, if the gain in the system or the describing function is complex, then we can use the Nyquist plot in order to analyze the stability of oscillations using describing functions. In the case of our example, we have this picture here. In this case, although the describing function was a complex one, we could get rid of that complex gain by putting this S here. So therefore, the gain at the end is a real and positive quantity. So therefore, what we can do here is that we can use actually the root locus plot in order to be able to determine the stability of the oscillations. So we know that at E hat is equal to 2 or minus 2, we have just oscillations, and the frequency of those oscillations are omega equals to plus minus 1. So here, for the sake of simplicity, I'm going to choose this mu parameter to be equal to 3. And then I'm going to be able to actually draw the root locus for the closed loop poles of this feedback system by changing k from 0 to infinity. So here, the open loop transfer function of this feedback system is everything in the loop. So I have k times this transfer function, where I substitute mu equals to 3. And then I can determine the open loop zeros and open loop poles. There is one open loop zero, and that is 0 here, s equals to 0. And there are two open loop poles, and they are given by these equations here. The number of open loop zeros is 1, and the number of open loop poles is 2. So in the root locus, there will be a number of asymptotes, and the number will be equal to 1 here. And the angle of the first asymptote is given by this formula, and it's going to be 180 here. Here I don't really have to calculate the angle between the asymptotes, but the formula for that is given by this. So we know that a point on the real axis is in the root locus if the total number of open loop poles and zeros to its right is actually odd. So these are actually all of the root locus rules that you have to know in EE404 in order to be able to use the describing function analysis for analyzing the stability of the oscillations that we obtained here. So now if I look at the root locus, I would obtain a figure like this. So I have real of S and the imaginary of S. I have the open loop poles here. We know that the root locus goes from open loop poles to open loop zeros or to the asymptotes. So here I have two open loop poles here and here, and one open loop zero at the origin, and the asymptote is actually here looking towards this side. So it has 180-degree angle, so it is on this line. So one of the closed loop poles is going to go towards the negative infinity here on this line here. So therefore there are two closed loop poles in this case, and we see that these two closed loop poles will start here at the open loop poles at k equals to 0, and then they're going to approach to each other for some k values, and then they're going to separate into two complex branches, and they're going to meet on the left hand side, and one is going to go to the open loop 0 and the other one is going to go to the asymptote. Here the real axis points are determined by this rule that I have used here. Here to the right, I have 0 open loop poles and zeros. Here to the right, I have 1 open loop pole and 0. Here to the right, so therefore this part is included because 1 is odd. And here I have two open loop poles and zeros to the right. So therefore I don't have any real axis contribution here to the root locus and etc. So we know that here at k is equal to 1, which is e hat square over 4, we have closed loop poles exactly on the imaginary axis. So these are just these 2 points, as you see. So therefore these 2 points are at j omega when omega equals to 1. So I have j here and I have minus j here. And when k is larger than 1, I have the closed loop poles going to the left, which means that I have a stable closed loop system. And when k is smaller than 1, I have some closed loop poles in the right half plane, which means that I have an unstable closed loop system. So, but you remember that we have already found these points, which are the j omega crossings, that we have found for obtaining sustained oscillations in the linear system. So now we are going to use this root locus in order to analyze the stability of the oscillations. So remember, these oscillations would correspond to these two points here. And remember, the stability of the oscillations means what is going to happen when we make the oscillations deviate from their original trajectories. Is the system going to go back to the oscillation, or it is going to get away from the oscillations further? So now let us try to analyze this type of oscillation here. The magnitude is E hat is equal to 2. This is the oscillation amplitude that we have found. Now what we would like to analyze is what is going to happen if I make this system, make this trajectory deviate from this oscillation just a little bit to the outside. Whether the trajectories are going to go back to the oscillation, or they are going to go away from the oscillation. So outside this circle, do I have a stable behavior converging back to the oscillation, or I have unstable behavior diverging from the oscillation? So what does it mean to make the trajectory deviate just a little bit towards outside the oscillation here? It means that I'm actually making this oscillation amplitude just a little bit larger from E hat is equal to 2. Let us now look at what is going to happen when E hat becomes just slightly larger than the original oscillation amplitude 2 here. So when E hat is larger than 2, then this linear gain that we have considered here, which corresponds to E hat square over 4, this becomes larger than 1. So remember, these imaginary axis crossings are representing our imaginary axis crossings are actually representing our oscillation here. So then we would like to understand what happens when k is larger than 1. When k is larger than 1, I know that the closed loop poles are going to go to the left of the imaginary axis. So in that case, I see that the closed loop system becomes stable. But we know that if I have a closed loop system which is stable, the oscillations in it are actually going to decay. So in that case, if the system is stable, I will have complex poles here in the open left half plane with negative real parts. And negative real parts means that the oscillations corresponding to these complex closed loop poles will be actually decaying, which means that E hat is going to get smaller in that case. So decaying means the amplitude of the oscillations will get actually smaller. So therefore E hat will be decreasing due to the dynamics of the system. So what do we understand from here? When I make the system deviate from its original oscillatory trajectory, making E hat larger than 2, the system dynamics itself makes E hat smaller and smaller until we reach back to the original reach back to the original amplitude 2 here. So therefore, outside this circle, I have a stable behavior which makes the trajectories, nearby trajectories, converge back to the original oscillatory behavior here. So therefore, the behavior outside the original oscillatory trajectory here is actually stable. But in order to be able to call the original oscillation stable, I need to make sure that the behavior inside the circle would also be stable behavior. So in order to be able to investigate that, we are now going to be looking at what happens when E hat is smaller than 2. This means that I make the trajectory, original oscillatory trajectory, deviate from itself just a little bit towards inside this circle. So therefore, in that case, the amplitude becomes just a little bit smaller than 2. And in that case, since this gain is equal to E hat square over 4, then this gain becomes smaller than 1. But what does gain being smaller than 1 mean? It means that the closed loop poles will go to the right hand side, and closed loop poles in the right hand side means that the closed loop system is actually unstable. So I will have two closed loop poles here in the open right half plane with positive real part. This means that these oscillations are actually going to grow in magnitude. So that means that when I have E hat smaller than 2, the system dynamics will increase E hat back to its original value, E hat equals to 2, which means that when we make the trajectories deviate from the oscillation here, they're going to be converging back. When we make E hat artificially smaller than 2 here, E hat is going to go back to its original value. So therefore, this means that inside the circle here, the oscillations are stable as well. So therefore, both outside the circle and inside the circle here, the oscillatory behavior is actually a stable behavior, which means that the oscillations are actually in the overall stable oscillations. So then when can we conclude that oscillations are unstable? For example, if when I make E hat smaller than 2, when k is equal to k is smaller than 1, if the system was stable, then E hat would continue to get smaller and smaller. So in that case, when I make E hat smaller than 2, the E hat would get smaller and smaller. So we would get divergence from the oscillatory behavior. Or if when E hat was larger than 2, if I had the system unstable, making E hat even larger, in that case the trajectories would be diverging away from the original oscillations here, making the original oscillations have unstable behavior here. But here in our example, we have actually stable behavior. So this is going to be all for this lecture. So in the next lecture, I plan to give some more theoretical derivations for the describing function analysis. And we are going to see the same topics that we have seen in this introductory lecture in more detail. So that's all for this one. Bye. Okay, welcome to the second lecture in EE404. So in this lecture, we are going to be seeing the describing function analysis in more detail. So far we have seen only the basics in the introductory lecture for describing function analysis on an example. Now what we're going to do is to see each part of that analysis in more detail. So the first thing that we are going to be doing is how to find the describing function of a nonlinearity. So let us now start with the fundamentals of describing function analysis. In describing function analysis, we have a system feedback loop in feedback loop form like this. So we have a nonlinearity here and we have a linear system connected to it, and we close the feedback loop. So most of the time there is a reference input here, and most of the time reference input is going to be equal to 0. So this is a nonlinear system in the overall due to the nonlinearity here, the nonlinear element, and we would like to analyze it using some linear control tools. We would like to understand when such a system would give us oscillations and when it does not. So for this purpose, what we would like to do is to use linear control tools. So what we would like to do is to replace this nonlinearity with some equivalent linear system. And this equivalent linear system, equivalent linear approximation of that nonlinearity is called the describing function. And we show it with the capital N here, and in general it is dependent on the amplitude of the oscillations and the frequency of the oscillations that we are going to be encountering here. And in general this is going to be, since it's a frequency domain quantity, this is going to be a complex number. So we will see when this is going to turn out to be a linear, real quantity, and when it is actually going to be a complex quantity with non-zero imaginary part. So now let us look at how to calculate the describing function of a nonlinearity. So for this purpose, we are considering a single nonlinearity here with the input E of t and the output U of t. So the procedure to obtain the describing function of a nonlinearity is pretty straightforward. So the first thing that we're doing is to set E of t to a sinusoid. So we set E of t as E hat some amplitude times sine omega t here. And then what we do is we use the description of this nonlinearity to calculate the output corresponding to this sinusoidal input. So what we know about this sinusoidal output would be that it is going to be periodic with the same period omega here as the input E of t. So, but the problem is it is going to have more frequency content than this single frequency at the input. So it is going to be periodic, but it is not going to be purely sinusoidal like the input. So it is going to have some higher order harmonics. So that is why after calculating U of t here, we expand it into its Fourier series representation. We know that U of t is going to be periodic with the same period as the input. So here it is Fourier series expansion would be possible. In the Fourier series expansion, we are going to have the terms like this. So we are going to have a DC term here that is called A0, and we will have sinusoidal terms at different frequencies. So for n is equal to 1, we are going to have the fundamental component. For n is equal to 2, we are going to have the second harmonic, third harmonic of the same fundamental frequency, omega here. So since this is a nonlinear element, there are additional frequencies in the output in addition to the frequency of the input here. If this was a linear system, then I would see only the frequency, a sinusoidal with the frequency the same as the input frequency here. But here we are going to have some additional frequency components due to the fact that this f is a nonlinear function. So now, in order to be able to simplify this analysis, in describing function analysis, we are going to make first two assumptions. The first assumption is that it is the assumption that A0 is equal to 0. So we assume that the DC component is equal to 0. And we're going to see that this is always going to happen if the nonlinearity f is an odd function. If the nonlinearity f satisfies this property, f of minus e, if it is equal to minus f of e, then we call f to be an odd function. And in that case, we are going to see that this A0 is always going to turn out to be equal to 0. So we have already seen some odd nonlinearities. For example, the relay that we have seen, or the saturation, or the dead zone nonlinearity. They are all odd nonlinearities. And in the case of those type of nonlinearities, we are going to have A0 equals to 0. So we get, with this assumption, we get rid of this term here. So later, at the end of describing function analysis, we are going to try to remove this assumption. So it is not necessary for describing function analysis, but for a simple exposition, I need this assumption first, and then I'm going to be able to remove it at the end of describing function analysis. So the second thing that we are assuming is that G of S has some low-pass characteristics. That means that here there will be a fundamental component and there will be higher-order harmonics. So we are going to assume that this system G of S actually attenuates all of the higher frequencies, much more than the fundamental frequency. So we're going to assume that the amplitude response at the fundamental frequency is much larger than the amplitude of the system at this higher order frequencies here. So there, with this assumption, we can see that we can actually neglect the higher order harmonics from this. We can take them out from this summation here. So we can say that the higher order harmonics will be attenuated by the linear system much more than the fundamental harmonic. So then we are going to be able to neglect all terms here corresponding to n2, n equals to 2, n equals to 3, etc. So that leaves us with the following output to the nonlinearity. So with these assumptions, we can say that U is approximately equal to A1 times cosine omega t plus B1 times sine omega t. And we know that this is the fundamental component of the output of the nonlinearity. In general, these Fourier series coefficients A1 and B1, they are dependent on our input amplitude and input frequency. So if I would like to use a better notation here, this U of t is approximately given as a coefficient dependent on E hat and omega times cosine, and coefficient dependent on E hat and omega times sine. Now, we are going to be able to actually think that this nonlinearity is a linear system. We will be able to approximate it with a linear system by thinking that this is the output of the nonlinearity to the input E hat sine omega t. So we can ask ourselves the question, what is the linear system which gives this output to the input E hat sine omega t? And last time in the example, we have seen that in order to be able to convert sine into a cosine, we need a system, linear system, in frequency domain represented by the complex number j. So by using this fact, we can actually calculate the frequency response of the system, which would give this output to the input E hat sine omega t. And I have an amplitude transformation from E hat to A1 and B1. So this amplitude transformation is actually represented by the division by E hat here. And I know that sine is converted into a cosine with the frequency domain representation J here. So therefore I have here A1 times J, and we know that in order to be able to convert sine into sine, there is no system. So it is just the system represented by the real number 1. So therefore, we have here in order to be able to convert E hat sine into B1 times sine, I need the system B1 over E hat in frequency domain. So the describing function corresponding to the nonlinearity is given by this formula. So here, in order to be able to find this describing function, all I have to do is to find the coefficients A1 and B1, and then I form the complex number B1 plus JA1, and I divide it with E hat to obtain the describing function of the nonlinearity. So let us remember the example that we have solved in the in the first lecture. So in that case, we have calculated the output of the nonlinearity to the input E hat sine omega t like this. So U of t was a constant here times cosine omega t minus cosine 3 omega t. So we are basically neglecting here this higher order term due to the low pass characteristics of the linear system, and then we end up with this approximate output. So this means that in this formula, the coefficient of cosine is E hat cube omega over 4, and coefficient of the sine omega t is just equal to 0. So B1 is equal to 0 and A1 is equal to E hat cube omega over 4. Then if I calculate the describing function using the formula B1 plus JA1 divided by E hat, then I would obtain this result, which was the result that we have found in the first example that we have solved. We solved in describing function analysis. Remember, we have reached this result in the example by making analytical trigonometric manipulations on the output U of t. So this is not possible in general. So what we're going to do in general would be to use the Fourier series coefficient formula. So in general, if you would like to calculate the Fourier series coefficients of a periodic function, you can use this type of formula. So the DC component is given by 1 over the period times the integral from 0 to the period U of t dt, and A1 is given as 2 over t integral 0 to t U of t cosine omega t, and B1 is given with the similar formula, but in this case, instead of cosine, we have a sine. So these are like inner products of U of t with the function cosine, inner product of U of t with the function sine, and inner product of U of t with the function 1 here. So you have to be careful here because there is a scaling difference here. The difference is caused by the energy of the function 1 is in general twice the energy of the function cosine or function sine here. Therefore, these coefficients in front of the integrals are actually different, and there is a scaling 1 to 2 difference between these two. Here, this t is the period of the function, and the frequency omega is given as 2 pi over t. So these formulas are good here, but we are going to need just simpler ones. So we are going to use them all the time. Here, one thing important is that here I can carry out the integration over any period of the signal. So I can take the integral here from 0 to t, or I can take the integral from minus t over 2 to t over 2 here. It won't matter because the signal is periodic with this period t here. So you have to keep in mind here that the integrals can be taken over any whole period, and the limits do not matter as long as you carry out the integration over one period of the signal. So I told you that we are going to change these. We are going to actually use different forms of these formulas, and we really do not want to deal with this period all the time in our calculations. So I will try to get rid of this capital T here and here by making an integral variable change. So here in this course, we're going to use modified versions of the formula for the sake of simplicity. So let us consider, so to see what we are going to do, let us consider the DC coefficient here, A0. So if I write this coefficient like this, then I have the same integral here. I multiply here the integral with 2 pi and divide the integral with 2 pi. So as soon as I do this, I get here 2 pi over t, which is going to be my frequency, and I will have 1 over 2 pi coefficient here. So I can therefore write this formula as omega over 2 pi times the integral that we started with. So now I'm going to take this omega inside the integral, and what I'm going to do is that I'm going to change the integration variable here. So I'm going to combine omega with dt here. And we know that omega dt is nothing but d omega t. So that is going to be the change in the integral that I'm going to be making. So since omega is constant, d omega t is equal to omega times dt. Therefore, if I take this omega inside the integral, then instead of this, I can write d omega t. But when I write this thing here, the omega t, then I need to change the limits of the integral as well. So the integral limits are from t equals to 0 to t equals to capital T. So I need to know which numbers correspond to omega t when t is equal to 0 and t is equal to capital T. And these numbers are simply when t is equal to 0, omega t is equal to 0. And when t is equal to capital T, omega t is equal to just 2 pi. Because omega is 2 pi over capital T times t, it is going to give me just 2 pi. So this is going to be the formula that we are going to be using in this course for the DC coefficient. I have a scaling constant, 1 over 2 pi, and the integral, now you see that both the scaling constant and integration limits are independent of the signal period, capital T. And we integrate u of t over a single period with respect to the variable omega t here. We're going to see why this is going to be useful to us. If I make the same manipulation on the A1 and A1 and B1 here, I would get this type of integrals. So I will have u of t cosine omega t d omega t, the integral from 0 to 2 pi, and remember that the coefficient of this one was twice the coefficient of the DC variable. So therefore the scaling constant here is going to be 1 over pi, and the scaling constant here is 1 over pi, and we have cosine and sine multiplications and integral with respect to the new variable omega t. Here I will make the same remark. So while calculating the Fourier series coefficients, integration limits can be taken over any period of the signal. So here in the integration limits I have from 0 to 2 pi, 0 to 2 pi. But I can take these integration limits over any period of the signal. So instead of from 0 to 2 pi, I can take the integral from minus pi to pi, or minus pi over 2 to 3 pi over 2, etc. So as long as you cover the 2 pi distance here, you are fine. So this is going to be useful sometimes to reduce the amount of effort that we spend for taking these integrals. So now we are going to be trying to calculate our first describing function. So here we are going to calculate the describing function of a relay. A relay is just a switch, and this is shown by the sine function like this here, and it takes the values plus a for positive inputs and minus a for negative inputs. So here I will always use a topology like this. So I will draw here on the upper left corner the nonlinear function that we are going to be trying to find the describing function for. And below that, I will draw the input. We know that the input is E hat sine omega t, and I'm going to draw E hat here like this. So let us look at this drawing. Here, because we are going to be taking the integration with respect to the variable omega t, this axis here of the input represents the variable omega t. So here I'm going to put the variables pi and 2 pi, one period of the signal sine omega t with respect to the variable omega t. So here, if I didn't make that integration variable change, then this axis would be t. Then I would have to use here capital T over 2, capital T over 4, etc. I would have to deal with these capital T's all the time in my in my input, and we would not like to do that. That is why we are using the variable omega t here in all of our plots. So this is our input to the nonlinearity, e hat sine omega t, and the sine function crosses 0 at pi, and it takes the maximum and minimum values at pi over 2 and 3 pi over 2 respectively, and it completes a single period at omega t equals to 2 pi here. So this is one period of the input of the nonlinearity. Now, what we are going to do here is on the right, I'm going to draw the output. The output is called u of t, and I'm going to be drawing it with respect to the variable omega t again. That is actually the integration variable. So that is why we are going to be drawing everything with respect to omega t. So this is my input, and this is going to be my output here. So now let us look at this nonlinearity. The nonlinearity gives positive a for positive input. So from 0 to pi, the input is positive or 0. Therefore, our response u of t of the nonlinearity is going to be plus a. And since the input is negative between pi and 2 pi, our response, the nonlinearity, is going to give us minus a between pi and 2 pi here. So this is our function u of t now. And now I would like to find the fundamental component of, in terms of the Fourier series expansion of this u of t function. So this is like a square wave, and I would like to find its fundamental component coefficients. So now let us start by calculating a0, the dc coefficient. dc coefficient is nothing but the integral of u of t, this function, with respect to omega t, and I need to do the integration from 0 to 2 pi. We know that this function takes the values a between 0 and pi and takes the values minus a between pi and 2 pi. So if I take the integral, this part of the function is going to cancel this part of the function, which means that the dc coefficient is going to be 0 here. So without taking any integral here, I can actually say that the dc coefficient is going to be equal to 0. And the reason for this is that this u of t is this nonlinearity here, relay nonlinearity, is an odd function. So it satisfies the odd function property, and we know that for every positive input value, there is a corresponding negative input value which takes which has the opposite signs here. So therefore, this integral would always cancel when this nonlinearity is actually an odd function. So now let us look at a1 here. a1 is the 1 over pi, is twice this coefficient, times the integral from 0 to 2 pi, u of t. I will multiply this square wave with cosine omega t, and then I will take the integral with respect to omega t. I have drawn here cosine omega t. So this is my cosine omega t, and I'm going to be multiplying this function, this square wave, with cosine omega t, and then we are going to take the integral of the multiplication. Here the interesting thing is that I see here that this function u of t between 0 and pi, it is symmetric with respect to the value of pi over 2. So here on this side I have a, and here on this side I have a as well. So, but cosine, it is odd around the value pi over 2. So for each positive value here, there is going to be a negative value on the other side of pi over 2. So therefore, when I multiply these two functions between 0 and pi, I will get an odd function around the value pi over 2 here. So for each positive value of the multiplication, I will have a negative value of the multiplication, which is going to make the integral cancel values of the integral from 0 to pi over 2 to pi over 2 to pi, they are going to cancel each other out. So therefore, the integral from 0 to pi of this multiplication of u of t and cosine will be equal to 0. The similar thing is going to be correct for the integral between pi to 2 pi. So we see that the function u of t is symmetric between pi and 2 pi around the value 3 pi over 2. And we see that cosine is anti-symmetric or odd around the value pi over 2. So therefore, when I multiply this function with the cosine, the resulting multiplication is going to be anti-symmetric or odd around the value 3 pi over 2. So the integral from pi to 2 pi of this multiplication is going to be again equal to 0. So we have here, therefore, this a1 is just going to be equal to 0, the result of this integral, because I can write this integral as for the integral from 0 to pi plus the integral from pi to 2 pi, and each of those integrals will give me 0 due to the symmetry properties of the multiplication, and the result is going to be equal to 0. So we see that this a1, the coefficient of the cosine omega t at the Fourier series expansion, will be equal to 0. The next thing that we are going to be calculating is the coefficient b1. b1 has the multiplier coefficient 1 over pi and integral from 0 to 2 pi u of t times, in this case we have sine omega t. So I go back to our figure. This is this function sine omega t, and I will multiply sine omega t with u of t, and I will take the integral from 0 to 2 pi with respect to the variable omega t. Again, here I see some symmetry properties. I see that sine omega t is positive here, and a is the u of t is a, positive, and sine omega t is negative here, and I have u of t is minus a, it is also negative. So here I can actually make some simplifications for the integral of the multiplication here. So here is what we are going to do. I'm going to take this integral. I know that these integrals, this is a positive times positive and negative times negative, they will give me the same integrals. So integral from 0 to pi is going to be the same as integral from pi to 2 pi of the multiplication of sine with this u of t. So therefore I can write this integral as 2 times the integral from 0 to pi. And the integral from 0 to pi is going to include a and sine omega t multiplication. I can take a outside, so I have here as the coefficient 2a over pi times the integral from 0 to pi sine omega t d omega t. So here, how should I take this integral? So the important thing that you should notice here, it is not really important what I call the integration variable here at this stage, because in the integral all I have is the integration variable omega t. So here what I can do is just replace the integration variable for not to get confused. Replace the integration variable with just t prime. In general, I will just replace it with t. It is not going to matter actually what I call. I can call it tau, I can call it u. It doesn't really matter. But here I just call it t prime, and in the future I will just change it into t. It's not going to cause any change in the value of the integral. So then this integral is the integral of sine t with respect to the sine t prime with respect to dt prime from 0 to pi. If I take the integral, it's going to be minus cosine t prime, and if I evaluate the result at the limits, I would just get 4a over pi. So now I can summarize the results that I have obtained, and I have obtained a0 equals to 0, because the function is odd, a1 is equal to 0, so the coefficient of cosine is equal to 0, and the coefficient of sine turned out to be 4a over pi. Now I can use our describing function formula, b1 plus ja1 divided by e hat here. So b1 is 4a over pi, a1 is 0, so this j is cancelling here, divided by e hat. So this is going to be my describing function corresponding to the relay element. So as a second example, we are going to be looking at a dead zone element, and this is going to be significantly more difficult actually because of the difficulty of the integrals. We need to be able to take some more complicated integrals in order to be able to calculate the describing function of a dead zone element. A dead zone element here is equal to 0 for e values between minus delta to delta, and it is linear for outside that range. And outside that range, we have the slope k here, and I have the slope k here. So this is called the dead zone element, and we have the same input to the dead zone element here. This is my E of t, which is equal to E hat times sine omega t. So I again draw the same thing here, and what I have to do is to calculate the output of this nonlinearity to this E hat input, E hat sine omega t. So I'm going to be drawing the output here. So the first thing that I have to consider is what is going to happen if E hat is strictly smaller than this delta. If E hat is strictly smaller than delta, then this sinusoid will be changing in the dead zone of the nonlinearity. So in that case, U is going to be completely equal to 0, which means that A0, A1, B1, they would be all equal to 0. So therefore, if E hat is smaller than actually this has to be smaller than or equal to. If E hat is smaller than or equal to delta, then the describing function is going to be exactly equal to 0. So therefore, the interesting thing here is going to be to assume that E hat is strictly larger than delta. So in that case, describing function is going to be non-zero, and we are interested in its value. So here, when we take E hat larger than delta, in that case, this point where this input sign actually is leaving the dead zone of the nonlinearity would be important. What is the angle m here? So remember that this axis represents omega t. So therefore, I have to find the value of omega t such that at that value, I call that value m, at that value, E hat sine omega t should be equal to delta. So here I have to solve the equation E hat sine omega t equals to delta, and I have to solve for omega t here in order to be able to find the value of m. So E hat sine m is equal to delta, therefore sine m is equal to delta over E hat, and this angle is between 0 and pi over 2, so I can take the arc sine here. Sine inverse delta over E hat is going to be my m. So now what I can do is to mark some other points. So this, when E hat sine omega t changes here, then it's going to come back and it's going to get back into the dead zone here at this value. And due to the symmetry here of the sine function, I know that the angle value at that crossing here would be pi minus m. Similarly, due to the symmetry properties, the angle value at which the sine leaves the dead zone on the left-hand side would be pi plus m, and the next time that it's going to be entering into the dead zone will be 2 pi minus m here. So now I can actually try to draw the output value. It is this figure here. So I mark here the important angle values: m, pi minus m, pi plus m, and 2 pi minus m. So until the E hat sine omega t reaches the angle m, we are in the dead zone. So the output is equal to 0 here. So this is my u of t, and it is going to be equal to 0 between 0 and m. Afterwards, we are going to be entering the alive zone, I can call it, and we are going to be having a non-zero response here. And since the response is going to be with respect to a line here, it is going to increase until the peak of the sine function. It is the pi over 2 here. We are going to reach a peak, and it's going to decrease back to 0 at this pi minus m. And between pi minus m and pi plus m, we're going to have again 0. And then we're going to draw the second non-zero zone here. It's going to be the symmetric or anti-symmetric component of this one. Anti-symmetric version of this one here. And then we are going to have a final 0 region here where E hat sine omega t is in the dead zone here. So the response is equal to 0. We are now almost ready to be able to take the integrals to calculate the coefficients A0, A1, B1. So here the missing thing is what is the expression for these non-zero regions here. Let us try to calculate the expression for this non-zero region. This expression is nothing but E hat sine omega t passing through this linear function here. And I have a line here crossing the point delta 0 here with slope k, and using the slope I can actually say that this line is going to intersect the y-axis here at minus k delta. So here, therefore, if I calculate the equation of this line, it is going to be k times e minus k delta here. So in k parentheses, it is going to be k times e minus delta. So therefore, I would have here the expression of this one. This non-zero part is going to be in this line equations. Instead of e, I'm going to substitute E hat sine omega t. So if I do that substitution, it's going to be k times E hat sine omega t minus delta here. This is going to be the non-zero part. And I know that this part is going to be the anti-symmetric of this version of this part. So now if I obtain the dead zone element equations here, if E is between minus delta and delta, then the output is equal to 0 for that zone element. And if E is larger than delta, then I have U is equal to, in K parentheses, E minus delta. And if I have the other condition, if E is smaller than minus delta, in that case, I would have U is equal to K times E plus delta. So now we are actually ready to calculate these coefficients. So now let us look at A0. A0 is the integral of U of t with respect to omega t between 0 and pi. When I look at U of t between 0 and 2 pi here, I see that the U of t between 0 and pi is equal to minus U of t between pi and 2 pi. So there is again an anti-symmetry with respect to the value pi here. So here, this means that the integral of U of t between 0 and 2 pi will be just equal to 0. So A0 is again going to be equal to 0. And remember, this was because of the fact that this nonlinearity is an odd function. It is anti-symmetric with respect to the with respect to the y-axis here. That is why a0 is equal to 0. Let us look at a1. a1 is going to be the integral of the multiplication of u of t with cosine omega t. I have again drawn this cosine omega t here. This is my cosine omega t. Now I want you to concentrate between 0 and pi. Between 0 and pi, this u of t is symmetric with respect to pi over 2. So for every value here, there is a corresponding symmetric value of u of t here. On the other hand, cosine between 0 and pi is anti-symmetric with respect to pi over 2. That means that when I multiply these two functions, I am going to get an anti-symmetric function with respect to the value pi over 2 between 0 and pi. This means that when I integrate that function, the integral from 0 to pi is going to be equal to 0. A similar thing is true for the interval pi to 2 pi. Cosine is anti-symmetric in that interval with respect to 3 pi over 2, and u of t is symmetric with respect to 3 pi over 2. So here you can just try to take the integral, it doesn't matter. But if you see this type of symmetric properties, you can actually just calculate this integral quickly to be equal to 0. So a1 is equal to 0 in this case as well. So when I look at the b1, I'm going to this time multiply sine omega t with u of t. And we see here that we have a similar property between 0 and pi and 2 pi. This u of t is anti-symmetric, and sine is anti-symmetric with respect to pi as well. So therefore, this integral is going to be twice the integral from 0 to 2 pi, 0 to pi, the integral of multiplication of u of t and sine omega t. So b1 is going to be 1 over pi, integral from 0 to 2 pi. I have u of t times sine omega t d omega t. Due to the symmetry or anti-symmetry results here, this is going to be twice the integral from 0 to pi. And here, can I do a better thing? Can I use more symmetric properties here? And the answer is actually yes. So now let us look at the integral from 0 to pi. If I integrate from 0 to pi over 2 only, the integral from 0 to pi over 2 will be the same as the integral from pi over 2 to pi, because sine is symmetric with respect to pi over 2 between 0 and pi, and u of t is symmetric with respect to pi over 2 between 0 and pi. So here, therefore, I can actually take only the integral from 0 to pi over 2 here and multiply the result with 4. There are 4 such integrals between 0 to 2 pi. So the actual result is going to be 4 times the integral from 0 to pi over 2. And now I can use where this function u is non-zero. So the multiplication of u and sine will be equal to 0 in these intervals where u is equal to 0. So therefore, I need to take the integral only between m and pi minus m. And in this interval, I know what this u of t is, and I know the sine function. So I will just multiply the sine function with this u of t in the interval m to pi minus m. So here, therefore, sorry, I'm making a mistake here. So I need to, here the integral was from 0 to pi over 2. So in this interval, the u of t is equal to 0. So here, I need to take the integral from m to pi over 2, not m to pi minus m. In that case, I would have multiplied the result with just 2, not 4. So I'm taking the integral from 0 to pi over 2. So therefore, in this interval, the only parts where u times sine is non-zero is between m and pi over 2. So now let us write this result. 4 times the integral from 0 to pi over 2, and I have 4 times the integral from m to pi over 2. And now I can write what u of t is in this interval, and sine omega t will remain there. So this is my u of t, and I have sine omega t d omega t here. So now I can make some manipulations. So first take this k outside. K is taken outside, and I have e hat sine square omega t here, and I have minus delta times integral of sine omega t d omega t. So now what I can do is that I can replace these omega t's with another variable, in order not to get confused. So let us change them into t. Now I have some straightforward integrals to take. In order to be able to take the integral of sine square, I will write this as 1 minus cosine 2t over 2, and the integral of sine t can be taken as minus cosine t, and that minus is going to cancel this one, and I will evaluate at the integration limits. So I can take this integral now quite easily. So this is all integration, just calculus. So it is unfortunately complicated, but we will have to deal with it. So when I evaluate everything at the integration limits, I would get this type of term. So here we get in the result we have sine m's, cosine m's, etc. So we have defined this m as the sine inverse delta over e hat. Now I can actually, using this result, I can actually write sine m is this one. And since this m is between 0 and pi over 2, cosine m is going to be given as 1 minus sine square root. So this is my cosine m. And I can actually substitute these results into the integral. So now if I continue in this manner, I'm going to get a complicated expression here. So you have to do this yourselves in detail as an exercise. So I have here k times e hat minus coefficient times sine inverse delta over e hat, and I have some other terms. So now let us summarize our results. A0 and A1 were both equal to 0, and we have found B1 to be this complicated coefficient. Now we can use our describing function formula in order to be able to calculate our describing function, B1 plus JA1 divided by E hat. So here, since A1 is equal to 0, this is going to disappear from here. So I will just have B1 over E hat, which is given by this formula. This formula looks complicated, but we see that here it is only dependent on the ratio of delta over E hat. So here you can actually try to guess what is going to happen if E hat goes to infinity. If E hat goes to infinity, this angle is going to be 0, and this term is going to be equal to 0, and sine inverse 0 is 0. So therefore we are going to end up with k as E hat goes to infinity. If I draw this describing function with respect to E hat over delta, if E hat was smaller than delta, then the describing function was equal to 0. And then it is going to start from 0 to increase to the value k here for very large E hat values here. So why does this describing function converge to k? Let us try to understand that. So here I want you to think about that the input is a very large amplitude sinusoid. If the amplitude of the sinusoid is very large, then I see that this m value is going to get smaller and smaller. So therefore these zero regions in the output will get smaller and smaller. And also this peak value, which is k times e hat minus delta, is going to be approximately k times e hat, because e hat is in that case very, very large, much larger than delta. So therefore this magnitude here is going to be k times e hat. So here, when e hat goes to infinity, this m is going to go to 0, and I would almost have here a pure sinusoid, and this pure sinusoid is going to be, I can actually express it as k times e hat times sine omega t. Here there has to be an e hat. There is a missing e hat here. So therefore, here, if I calculate B1 when E hat is very large, I would get K times E hat. When I divide it with E hat, I'm going to get K as my describing function, since A1 and A0 are both equal to 0. So you can think about describing function as a complex game here. When E hat is very, very large, the input is just multiplied by just k. So the describing function just becomes equal to k, because this resulting output in that case is k times e hat times sine omega t. So then describing function, if e hat is very large, it converges to the value k here. So far, the describing functions that we have found turned out to be both real. So, and the realness was caused by the fact that a1 was equal to 0 for both cases, for both examples. Actually, there was a reason, a very, very clear reason for this. It was because that these nonlinearities were actually static nonlinearities. So they were memoryless nonlinearities. So for a single e value, we had only a single u value. So the nonlinearity did not have any memory in it. That was actually why we got real describing functions for both of these examples. Now let us try to understand this fact. So suppose that I have a static nonlinearity. It really doesn't have to be an odd nonlinearity for a1 to be equal to 0. So here, suppose that I have a static nonlinearity which is equal to a constant a for positive e, and which is equal to this line for negative e. So now I would like to draw the output corresponding to this input here. It is the usual input that we try. When I draw the output, I'm going to be wondering about the value of A1. What is the coefficient A1? And here, by just making similar symmetry analysis in the output, we will be able to say that for this type of nonlinearities, for static nonlinearities, we will always get A1 equal to 0. So for only dynamic and nonlinearities with the memory, we can have complex describing functions. So what does a static nonlinearity mean? It means that for a single e value, I have just a single u value. And you see that for a single e value, for this nonlinearity, I always have a single u value. So what can make this nonlinearity have multiple values at a single u e value? It is a type of hysteresis type of nonlinearities, for example. With hysteresis type of nonlinearities, for a single e value, I can have multiple u values depending on the derivative of the input. So this derivative is a form of dependence on the derivative is some form of memory. So therefore, for those type of multiple valued nonlinearities, for nonlinearities with memory, we will have complex describing functions. But you see that for this nonlinearity, for each e value, I have a single u value on both sides. So this is a static nonlinearity. And what does this bring to us? So this brings to us the following. let us concentrate between 0 and pi. Between 0 and pi, sine function is symmetric with respect to pi over 2. Okay, between 0 and pi, sine function is symmetric with respect to pi over 2. So for each value on the left hand side of pi over 2, there is a symmetric value at the other side of pi over 2. I know that for each of these values, the nonlinearity gives me the same response, because the nonlinearity gives me the same response for the same E values. Since these two E values are the same around the value pi over 2, the corresponding output values will be the same. So since the sine function is symmetric with respect to pi over 2 between 0 and pi, if I have a static nonlinearity like this, its shape really doesn't matter. It can have any other shape here. As long as it is single valued, as long as it is static, the output will be symmetric with respect to pi over 2 in the interval 0 to pi here. So the similar thing is actually correct for the interval pi to 2 pi. So in that case, the sine function is again symmetric with respect to 3 pi over 2 this time. And since the nonlinearity is static, the output between pi and 2 pi will be symmetric with respect to 3 pi over 2. So due to the static property of the nonlinearity, here this specific nonlinearity is not really important. You can think about any nonlinear shape here, as long as it is single valued, as long as it is a static nonlinearity, the output u of t in the intervals from 0 to pi will be symmetric with respect to pi over 2, and in the interval from pi to 2 pi, it will be symmetric with respect to 3 pi over 2, due to the static property of the nonlinearity. And I know that cosine is anti-symmetric with respect to pi over 2, and cosine is anti-symmetric with respect to 3 pi over 2. That means that when I multiply cosine with this u, and if I take the integral, I will get 0 for the integral from 0 to pi. And similarly, I will get from pi to 2 pi, the integral will be equal to 0, because the multiplication will be anti-symmetric with respect to value pi over 2 and 3 pi over 2 here. So this is the result here. So I have a1, this integral is always 0 for static nonlinearities, and this integral is always 0 for static nonlinearities. So a1 is equal to 0 for static nonlinearities. So I have tried to write these results here. So u of t is even, symmetric, around pi over 2 in this interval. So u of t is even around 3 pi over 2 in this interval. And cosine is odd around pi over 2 in this interval. And it is odd around 3 pi over 2 in this interval. So therefore, these multiplications are odd around pi over 2 and 3 pi over 2 in these intervals. So these integrals would always be equal to 0. So now what we have obtained at the end of this analysis, we have really said important things here. First of all, if the nonlinearity is static, then a1 is going to be equal to 0, which means that the describing function is going to be real. If the nonlinearity is odd, then a0 is going to be equal to 0. So we have, if the nonlinearity is both odd and static, then I can calculate the describing function n of e hat, and its imaginary part is going to be equal to 0.